Hi everybody, it's Mr. Garrett, and we're going to go ahead and do another fun and exciting lesson. We're going to start a new unit on polynomials, and we've actually already been working with polynomials for a chapter now, quadratic polynomials, and actually if you think back 2 or 3 chapters when we were talking about linear polynomials, you just knew them as quadratic functions and linear functions. But now we're going to get into other degrees of polynomial functions, and the first thing we need to work with is exponent properties. The better we can work with these, the better off we're going to be. So we're going to go ahead and start with that, and hope you enjoy. So the first thing that we're going to talk about here is the exponent properties. And the exponent properties, there's a couple of them. It looks like, oh my gosh, I'm going to have to learn all these and memorize them, and yes and no to some extent. Obviously, these each have a name. For example, this one here is the product of power property, and this is the power of product property, and this is the quotient of powers, and this is the power of quotients, but nobody's going to expect you to memorize those actual names of them. What I really want you to do is be able to work with them and evaluate them and use these properties to simplify exponent expressions. So basically there's a couple general things that we can do. One, when we see something like this, it's the power of products or the product of powers or whichever one it is, but we see multiplication and the bases are the same. That's always important. When the bases are the same, when we multiply, we add the exponents. So multiplication means to add. Down here, when we're dividing, again, the bases are the same, we subtract. So addition, add, divide, subtract. Should be pretty common sense. Over here, we're distributing. When we have multiplication, we can distribute exponents. Now, we can't distribute exponents when we're adding or subtracting, but when we're multiplying or even dividing, we can distribute those exponents, and you can see like ab to the n is a to the n times b to the n, or a divided by b to the n is a to the n divided by b to the n. So addition, subtraction, can't distribute. Multiplication and division, we can. When we get down here to a problem like this is the only one that we call by name a lot. This is a power of power property or a power to a power property. And whenever we have one exponent raised to another exponent, we multiply those. Multiplication means to add, division means to subtract, power to a power, we multiply the exponents. The last couple here are pretty straightforward. Anything raised to the 0 power is 1. Anything raised to the 1 power is itself. Very common. There's theorems and proofs of why that is, but just take my word for it. Anything to the 0 power is 1, and anything to the first power is itself. And then finally, down here, this one, when we have a negative exponent, whether that negative exponent is on the top or the bottom, we flip where it's at. For example, this a to the negative n, that's on the top. So we flip it, put it on the bottom, and make it positive. If we were to have, say, 1 over a to the negative n, then that would then go on the top, like that. Okay? So what are we going to do with these? We're going to go ahead and we're going to use it to evaluate or simplify or whatever else we need to do. Evaluating and simplifying being the key components. So I shrunk it down, put them over here. We're going to use that as reference, but we're going to work with these over here. And right now you can see that we have 4 to the second to the third power. Well, this is a power to a power property, just like we have right here. Anytime we have a power to a power, we multiply those exponents. So 2 times 3 is 6. So now we're looking at 4 to the 6th. I'm sure many of you are going to go to your calculator, type in 4 to the 6th, and you're going to find that it's 4096. And that's our evaluated answer for 4 squared to the third power. Now, but what about order of operations? Well, that's true. We could do order of operations. We could first do 4 squared, and that would be 16 to the third power. Now, do you know 16 to the third power? No, but you're probably going to go ahead and put it in your calculator, and you're going to get 4096 again. So either way we work at it, it works out to be 4096, and that's a good deal for us. All right, let's try another one. Negative 8 to the first power times negative 8 to the third power. Now, even though there's no 1 there, I'm going to write it in there because what happens when we multiply? When we multiply, we add the exponents. So we're actually going to have negative 8 to the fourth power. Now, when you plug this into your calculator, be very, very careful. Make sure that you use parentheses, because if you don't, you're going to get an answer of negative 4,096. But any negative number raised to an even power is a positive number. So we get 4096. Again, what about order operations? Well, if we don't use the exponent rules, we would have negative 8 times, and negative 8 to the third power is going to be negative 512, like that. And negative 8 times negative 512 is, again, 4096. So this is just like saving us a step, or at least looking at it in another way, and that's always key. All right? Anybody want to take a guess as to what 2/9 to the third power is? It's not 4096. So anyways, we're going to go ahead and we're going to take this exponent, we're going to distribute. We're going to distribute here and here. So we're really going to have 2 to the third power over 9 to the third power. 2 to the third power is 8. You should know that. 9 to the third power is 729. Bonus points if you know that. And then just leave it. There's nothing else that we can do. So we're just going to leave it as 8 over 729. And then finally this one, this is kind of like scientific notation, which we'll hit on a little bit later. But what I would want to do is I want to group the 6 and the 9 and group the 10 to the negative 4th over 10 to the 7th. Because 6 over 9 reduces to 2/3. That's pretty straightforward. These here, we have subtraction. When we see subtraction, we see division, we subtract. All right, and that's going to be times 10. Now, negative 4 minus 7 is negative 11. All right, we can leave it like that, or we could go ahead and put it on the bottom and say 2/3 times 1 over 10 to the 11th. Thing is, we're going to keep it like this because, again, that's scientific notation. We'll talk a little bit about that as we get going on. Now, I already know your question. If we can do this all on the calculator, why do we even have to know the exponent properties? And you're right. With the exception of, unless you have a fancy-dancy calculator, you don't have a calculator that will work with exponent properties. If you have a computer CAS calculator that does algebraic expressions and simplifying, then you're right. You don't need to know these. But most of you have just regular old calculators or graphing calculators, and you need to know the properties. So let's get into some with the variables. If we first look here at x to the negative 6th times x to the 5th times x to the 3rd, all multiplication means we add exponents. So really, I'm going to look at this as x to the negative 6th plus 5 plus 3. Well, negative 6 plus 5 plus 3 is x squared. And that's my result. You don't have to show this part, but I'm just showing it right now so you can see where I got that stuff from. All right. The next one, 7y squared z to the 5th times y to the negative 4th z to the negative 1st. Well, it's all multiplication here. So even though they're grouped as here and here, we can take away those parentheses and we can group. So it's 7y squared y to the negative 4th. So I'm grouping my y's together. Z to the 5th and z to the negative 1. Now I'm going to look and I'm going to say, okay, 7 is by itself. I have y squared and y to the negative 4th. Well, multiplication, same base. That's going to be y to the negative 2nd. And then z to the 5th, z to the negative 1, that's same base, multiplication, so we add, and I get z to the 4th. Now what do I do with a negative exponent? Oh yeah, negative exponents we put on the bottom. And so now we get 7z to the 4th y squared as our solution. All right. Over here we got two other ones. These look crazy because they're fractions. Everybody loves fractions. They're personally my favorite, but we'll go through and kind of get you used to them. Here we have s cubed over t to the negative 4th all squared. Well, when I see that, what I'm going to do is I'm going to distribute. And I'm going to say s cubed squared over t to the negative 4th squared. Well, power to a power means I multiply. It's going to give me s to the 6th over t to the negative 8th. Now what do I do with a negative exponent on the bottom? I bring it up to the top. S to the 6th, t to the 8th. And that's my final answer. All right. One last one over here. Again, there's two ways that we can do this. The first way I'm going to do is I'm going to distribute. I'm going to say x to the 4th to the 3rd, y to the negative 2 to the 3rd, over x to the 3rd to the 3rd, and y to the 6th to the 3rd. Power to a powers means I multiply x to the 12th, y to the negative 6th, over x to the 9th, because 3 times 3 is 9, and y to the 18th. Now I have x's here, same base, so I'm going to say 12 minus 9, that's x to the 3rd. Here I have y to the negative 6th over y to the 18th. Negative 6 minus 18 is y to the negative 24th. And the last thing I'm going to do is write it out so that x to the 3rd is on top, y to the 24th is on the bottom. Now, there is another way that we go about doing this one. If you want to, you can do it that way. It's just simplifying before we raise it to the exponent. So if I see this, x to the 4th over x to the 3rd, that's really just x to the 1st. And here if I see y to the negative 2nd and y to the 6th, and I subtract, I'm going to get y to the negative 8th. Now, with that being raised to the 3rd power, I can distribute that exponent, and I can get x to the 3rd, y to the negative 24th. Take that y to the negative 24th, and we put it on the bottom. Sorry for the penmanship there. Okay? So we need to be able to work with these exponents and simplify properties like that. And then the last thing that we're going to talk about is scientific notation. Scientific notation is really good for really big numbers or really small numbers. And by really big numbers, we're talking like millions, billions, trillions, quadrillions, so on and so forth. The key is every time we write it out as c times 10 to some power, where c is between 1 and 10, and n is an integer, meaning positive 2, positive 3, negative 7, negative 4, whatever. Okay, just not a decimal. It's very easy. I'm sure many of you have done this before. But when we see something like this number is 85 million. What we're going to do is we're going to put the decimal point right here between the 8 and the 5. Okay, and that's going to be 8.5 times 10 to some number. Now, since it's a really big number, we got to make our exponent positive. And the way that works is we go, okay, 1, 2, 3, 4, 5, 6, 7. We move the decimal place 7 places to the left, and so now that means our answer is 8.5 times 10 to the 7th. If you try it with this one, we're going to say, okay, well, the decimal point has to go between the 1 and the 2, so it's going to be 1.2 times 10 to the, how far do we move the decimal point? 1, 2, 3 spaces. So 1.2 times 10 to the 3rd. Now with really small numbers, what we're going to do is we're going to take and still put the decimal point between that first number and the rest. So this is going to be 2.3, but now we're moving it to the right. 1, 2, 3, 4 units to the right, so it's going to be negative 4, so 4 decimal places. All right, here we're going to have 5.67 times 10 to the 1, 2, 3, negative 3rd. Negative exponent means the number is really small. Positive exponent means the number is really big. Down here, we're looking at scientific notation. We want to put it as regular notation. So 1.02 times 10 to the 11th is going to be 1 point. Actually, we'll erase that. Hold on. We're going to go ahead and say it's 102. 102. Now, if I moved it 2 spaces already, 1, 2, I got to move it 9 more spaces. 3, 4, 5, 6, 7, 8, 9. So now I have 9 spaces between where the decimal place was and the end. Actually, I need to make it 2 more. Oops. So we're going to go ahead and we're going to add in another 0 here and another 0 here. So there's my next comma, 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 and so on. All right, kind of messed that one up. Sorry about that. Let's do this one. Anybody know this? 6.022 times 10 to the 23rd. It's Avogadro's number. It's really big. 1022214. I've moved the decimal place 1, 2, 3, 4, 5 places already. I got to get all the way up to 23. So I say 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. And there's thousands, millions, billions, trillions, quadrillions, quintillions, sextillions. All right, so 602 sextillions is how many atoms are in a mole. All right, down here, now we were looking at really small numbers. So we got 6. If I take that decimal place and move it 1, then 2, 3, 4 spaces to the left, you can count 1, 2, 3, 4 spaces, and we're good to go. Down here again, 0, 2, 3, 4, 7, 1. Decimal place was here. I move it 1, 2. That's how we get it. Okay? Scientific notation, remember, if it's a positive exponent, it's really big. If it's a negative exponent, it's really small. So I'm hoping that helps out. We're going to do some activities in class tomorrow that will hopefully reinforce this, give you some time to practice, and we'll talk about Scrooge McDuck and some other fun things that can deal with scientific notation. Hope you enjoyed.